Okay, hi guys. So in this lecture, we'll be starting off with photoelectric effect. Okay, so which is basically uh, again stimulates the particular nature of light. Okay, so let's get started with photoelectric effect. So underlining it actually derives from the fact that consider particle nature of light. Okay, and let's get started. So suppose we have a circuit. Okay, this is negative charge battery and this is positive charge side of the battery. Okay, so what we'll do is we have connected this to a cathode metal plate. This is a metal plate. Okay, and this is a cathode. Okay, so nothing but negative charge emitter. Okay, and on this side also we have connected a plate which serves as anode or electron collector. So what happens now is electrons move from negatively charged cathode plate to positively charged cathode plate. So this will serve as negative electrode, and this would serve as positive electrode. Okay, so when light of appropriate frequency is incident on the metal surface, electrons get ejected from the metal surface. This phenomena is called photoelectric effect. So hence the ejected electrons from the metal surface are called photoelectrons. Okay, so I'm just writing this line over again here, that when light of appropriate frequency is incident on metal surface, electrons ejected from the metal surface, or other electrons are ejected from the metal surface, and this phenomena is called photoelectric effect. Okay, and the ejected electrons from the metal surface are called photoelectrons. Okay, and according to the Einstein, light consists of a stream of particles which is called photons. According to Einstein, light contains, or light rather consists of, stream of particles called photons. Okay, and another point is that the energy of incident photons is the minimum energy required to eject electrons from metal surface plus kinetic energy of the ejected electrons or ejected photons. So how much energy? Okay, I think I have missed a point over here, that this is on this cathode ray or on this cathode plate, we are photons are actually incident on this cathode surface. As a result, electrons are getting ejected from the cathode surface. Okay, so how much energy of incident photons we require? Incident photons, not electrons. So we require the minimum energy or the activation energy. You can also frame this like this, that the minimum energy required to eject electrons from metal surface plus the kinetic energy of the electrons with which they are getting extracted out. Okay, so this incident energy of photons is required for these two purposes. Okay, we can also say that E equals to energy required plus half mv square. Okay, so mass m is the mass of electrons and v is the velocity of photoelectrons. Okay, so h nu would be equal to h nu naught plus, I'm just extending this definition, plus half mv square. Okay, or you can rather say it that hc by lambda equals to hc by lambda naught plus half mv square. You can also calculate, if you have been given these two energies, you can also calculate the velocity of ejected photoelectrons. So half mv square equals to h nu minus phi. Phi is the energy required. I'm just denoting it with a symbol phi. Okay, energy required, but I'm just writing it as phi. Okay, so let's define next the threshold energy. Okay, threshold energy is the minimum energy required for the ejection of electrons from metal surface. Okay, so minimum energy required for ejection of electrons from metal surface. And the corresponding minimum frequency is called threshold frequency. Okay, so now E naught is the threshold frequency and mu naught would be, oh sorry, this is the threshold energy and this is threshold frequency. Similarly, lambda naught is nothing but threshold wavelength. Okay, so next let's draw a graph to understand this better. That on a x-axis let's have frequency or nu, and on y-axis let's have kinetic energy of ejected electrons. Okay, on y-axis. Okay, so this is nothing but h nu naught, and this is the minimum energy which is required for the kinetic energy to be at 0. So this is nu naught, and afterwards we have a slope of h, okay, as half mv square equals to h nu. So this is a graph between h nu minus h nu naught. Okay, so just compare it with the equation of y is equals to mx plus c. We will get to know that m is h and c is minus h nu. Hence at x is equals to 0, kinetic energy would be minus h nu. Okay, I'm not showing the minus sign here, but I'm just showing the maximum magnitude of the point from the origin to the negative y-axis. Okay, so 3 cases come up here, that if nu is less than nu naught, then number of electrons, then no ejection from of electrons from metal surface. Second, we have that if nu equals to nu naught, then kinetic energy of ejected electrons would be 0, and case 3 would be definitely and obviously nu greater than nu naught, then it would be kinetic energy has, or other electrons is kinetic energy of electrons is positive. So one more thing here is, so more the energy of photons, more would be the energy transferred to the photoelectrons. Okay, so with this we come to the end of this lecture. In the next lecture we will be discussing on intensity of light. So till then, good luck and goodbye.